Sure, we'll cover some announcements. Welcome back to CS 198-126. This is lecture 12, I believe. Some announcements. Quiz 5 is due tonight. Quiz 6 has been released. It's due next Monday, as always. Homework 2 is due this Friday. I would suggest starting it if you have not done so already. This is slightly longer than homework 1, and we are not going to be as lenient with extensions as we were with homework 1. Other than that, I'll let Kate take it away.
Sorry, can you repeat that last part about the extensions?
I'm just saying that we will not be as lenient with extensions with homework 2 as we were with homework 1.
Okay.
So it's due this Friday. You should start if you have not already.
Right, but do we still have the extension time, or is that?
No, this is the extended deadline. Friday right now.
Friday is the extended deadline?
Yeah.
Okay, thank you.
Awesome. Can everyone hear me well enough? Perfect. So about a week ago today, I started us off talking about sequence models, and in particular, how they will then go and be applied back to vision. And for the first time, I can actually follow through on my claim that sequence models impacted vision and that they impacted them positively because of compute. So I set us up for sequence models explaining how they work. Then last Wednesday, you saw the transformer and you saw what made the transformer successful. Today, we're going to be just simply combining the two ideas, going over a little bit of literature and seeing why, in particular, transformers make a great solution for computer vision. So let's get into the motivation. I built up a whole lecture on sequence to sequence, or just generically representing any sort of time data or data in a nature that's not necessarily spatially related. And we're now going to show how that kind of thinking can be brought back to images. And the main statement at the time when the initial VIT paper, Vision Transformers, was released was that transformers work really well for text. How can we make them also work for images? Oh, my bad. I'm geriatric, forgive me for that part. Okay. So transformers work really well in text. How can we make them work for images? And then it's going and abusing the very nice properties that transformers have in particular. And that kind of leads us to why we wanted them, period. So the nice thing that we'll show at the end of this lecture is that transformers have very nice scalability, as we can kind of see from natural language and in the transformer lecture. But one other very fun thing is that they also have great global receptive fields. If you think about convolutions, you can only see what sequential layers have been able to patch by patch intersect and interlock over. But for the first time, you can actually see the whole image all at once. And this allows you to do way more complex calculations. And as they show in the initial paper that derives vision transformers, you can start making use of these features super early in the model and deriving very, very high performant downstream tasks. So let's go back to the transformer architecture, where it all starts. And we'll also discuss where we diverge from what we're going to do today. So we start with text. Text, as we discussed, is tokens. So a bunch of one-hot encoded sequences. Instead of using text, we have to use sequences, which get turned into vectors, and those vectors get turned into integers. When you have those integers, you can then look them up into an embedding vector table via a dictionary. Then what we do in order to understand where exactly in a sentence each token is we add an additional embedding vector. And we got through that with sinusoidal position embeddings. Next, what we do is we do a forward pass through a stack of transformer layers. This is the very challenging and weird part about the whole transformer architecture, is that it proposed these sort of operations that you don't see often in the rest of the field. You could kind of view that as a conglomeration of multiple past papers leading up to it, but until then, it was very new and very foreign, and still kind of is when you look at it in comparison to what people propose today. So you can kind of black box that part, but just keep in mind it takes in sequential data and will output more sequential data. But the fifth thing that makes the transformer very interesting as well is the CLS token, or the class token. This represents a single token that will be held constant throughout all of inference time and can then be used for more generalizable tasks in the future. With BERT, for example, that was the predicting whether or not two sentences actually follow one another, predicting whether a sentence is belonging to a certain class if you're doing positive or negative sentiment analysis. And the reason you fix that token and keep it constant is because if you just use the vectors alone, the vectors might change, and your model has a big problem of where should it store some long-standing information. You can almost think of this like a register, so to speak, in computer memory. You're giving your model a single place that it can store a lot of information and hold it constant over time while it's evolving throughout the course of its operation. And finally, we get into the classification head, which is literally a linear layer that's often passed on top of the CLS token. So you do transformer inference, you have your CLS token, and that CLS token will output a vector. Then let's say we're doing sentiment analysis. We simply just learn a linear classifier on top of the vector representation of the CLS output. And that's how we're going to do perhaps logistic regression, or even supervised fine-tuning if you want to train the whole transformer end-to-end on a supervised task. And then there's many ways to do this. There is self-supervision. You could train a GPT-style model going just to the next token. You could train it with BERT, masked language modeling objective, many things, many powerful ways to pre-train this architecture. But the story of it all is that it was founded in sequential data, and we now have a bit of a mental shift that we need to make to apply this to images. So we don't have text tokens anymore. So this exact part, it's the text embedding vectors that we could rely on beforehand. We no longer get to make the same assumption as work with images. When you're doing images, you have pixels, oftentimes 224 by 224, 3 color channels. If you represented every single possible combination of just a single pixel, you have an insanely large vocabulary. And one paper that kind of accepted that, but broke it down a little bit more, is called Image GPT. They call it generative pre-training from pixels, kind of a play on OpenAI's generative pre-trained transformers, or GPT-3, the GPT-N series that OpenAI put. And they took that similar approach, this time using images. So as we discussed, pixels are kind of discrete. That's at least one nicety that we've gained from text alone. But how do we actually go and relate pixel values onto a discrete vocabulary like we did in text? We could treat each color value like a separate word in our vocabulary, but then the combinatorics don't play nicely. Each pixel is 24 bits, 8 for each color channel. And with 3 color channels, exponentiating that and representing every possible space, you get over 16 million potential vocabulary tokens. And that's slow to learn representation-wise, it's sparse, it's not dense. There's a lot of challenges that would occur if you were to go with just this very naive solution to generating vocabulary for your transformer. But this is where we get interesting. You don't actually need that many colors. And so the inductive bias that ImageGPT proposes is that maybe we can get away with less. What if we only use 9? In particular, we have integers ranging from 0 to 8 for all 3 of the color channels. And we use that instead to decompose new vocabulary. And that works. Vocab size of 512 fulfills our goals as now computationally feasible, and we can get off to the races. But the next kind of weird thing that we do to make this paradigm align with what we've previously done is we read pixels in roster order. We go row by row from the top left corner all the way to the right, then to the next row down, all the way from the left to the right, so on and so forth, in order to get our input sequence. So it's kind of like we took this 2D image, flattened it into a singular vector, and then trained almost like a text transformer on that. And this is where we get into another issue. As we'll see today, there's many issues and there's many solutions for how we can overcome these issues. But the first major one now that we're doing with transformers is time complexity. Convolutions are fairly cheap. Transformer operations, not so much. Though they fit with the hardware that we've developed and they fit with the modern accelerators, they still don't fundamentally overcome the fact you have to compute things. And computing many things in series is not fast. So transformers are O of n squared with respect to input length. And O of n squared with respect to the length of each side. So we get an O of n to the 4th kind of issue with the actual size of our images if you take n being like the number of pixels in the image, or n being the dimensionality of your initial image. So if it's an n by n image, you now have n squared total tokens. N squared total tokens squared again for the complexity of the transformer gives you an even bigger blow up. And that's not optimal. Then again, we have one more silly solution, and that's kind of just to downsample it. Other models in our class, instead of having like 256 by 256 tokens, if we just treated every image as each pixel being there, we'd end up with over 65,000 tokens, while BERT, in comparison or in contrast, only has 512. So how do we go and close the gap? And for this one, there's actually a really simple solution. We haven't done anything brilliant just yet, and it's just to use smaller images. Less pixels, less tokens, it works. Nothing groundbreaking just yet, but where it gets fun is some of these results. So max size is 64 by 64, and then you train it exactly just how GPT was trained. You heard me harping about a week ago saying, just predict the next token. Why not just predict the next pixel? You've given yourself an unsupervised image learning task. You can now just go and basically give half of an image and tell it to predict the bottom half. And you've given yourself a task to pre-train on. You can do it super quick, super speedily, because remember, transformers, at least during the pre-training step, they can do inference all at once using causal masking and getting this notion of time without having to unroll into a for loop, and that's nice. So we get to enjoy those benefits, and we've reframed our task to fit the constraints. And now what happens? It works well. You get nice image representations from maybe the weirdest thing I could tell you to do, which is take an image, flatten it, get rid of all notion of position, and then go crazy. And it gets state-of-the-art on semi-supervised classification. So limited label samples, you train just a linear classifier on the representation that's derived from this model. The representation actually comes from the middle layer because during their ablation studies, they're like, oh, by the time you get to the final output, those vectors are too muddy. You can actually just peek into the halfway through the transformer and pull out a better representation that's more generalizable towards the classification task. And they get really competitive results with other things. But the big trade-off is that they use a lot of compute. And the other thing they do in line with most computer vision papers is they have some really pretty pictures for us. So for example, what I was talking about before is if you give it half the image, like you give it the top half, because the way we trained this model is that it predicts what goes forward in time as soon as the image is flattened. With the top half, it can go and predict the bottom half. And then you can get many different potential outcomes just from sampling from this transformer. Basically, exactly how we sample from language models today. But now let's talk about the bad. This uses lots of compute because we were very naive in the way that we actually went and defined each token. Defining each token as a pixel led us into the probability of O of n to the fourth that we discussed beforehand. So now the next question becomes, how can we kind of overcome this? And how can we do something a little bit better? For more about the compute, they train many different sizes, one at 6.8 billion parameters, which is what most people are open sourcing like large language models today. And doing that, especially at this size, this model size, and this many tokens is insanely expensive. 25,000 V100 days. At the time, V100s were more expensive, but about now you can get a single V100 for about $1 an hour if you do the napkin math there. So 24 times 2,500, that's the number of dollars that they had to spend to train this model. All to get kind of okay performance in comparison to just ConvNet that you could have run on your laptop. We have to make some sort of justification for why we want to use these models in the future instead of just sticking with what we already have. And in particular, MoCo as the comparison point can be trained in only 70 V100 days. 24 times 70 equals the number of dollars. It's very cheap. If I was an R&D manager at a company, I know what I'd be paying 10 times out of 10. And last but not least, we only got 64 by 64 pixels. So we're left at a crossroads. We have a very fun new way of thinking about images, but we have not yet hit the computational efficiency that we need to justify this. How can we overcome that? And how can we spin this task in a new way to derive a more efficient model that scales better, that you can go and justify to your boss, or at least justify to other scientists at the end of the day? This is mostly just a proof of concept. And with that, the proof of concept showed that massive self-supervised training can be applied to many new domains, and we can kind of leverage this in our new solution. And it's very important that we take this into account, this particular self-supervised stage, because this is what's going to let the next breakthrough that I talk about actually go and do its magic. And one more final aside, there are ways to make transformers more efficient. You can modify the attention operation. There's many funny little things you can do in the middle to just make this all go faster. But the thing that we really like at the end of the day is that these are just huge matrix multiplications that you do. And the model is very simple. And whenever we have to kind of stray away from that, we're losing a lot of the complexity that we derived and got to enjoy the first time we derived the transformer architecture. So our goal is to stick with the initial transformer, but not to lose everything that we gained along the way that made it great. And now we get to the more practical solution. This is the one where I can finally like stand behind and say, we've done something fundamental and foundational. I made a great promise that the world of computer vision was rocked by a singular paper, in particular, decomposing an image into 16 by 16 words. Their flashy title is "An image is worth 16 by 16 words." What they propose is that you can treat an image just like text, but you can do it better than Image GPT did. And that's by actually just taking strided convolutions across the image, feeding that all into the transformer at once. And that is how you can solve computer vision in a very computationally efficient way that satisfies all of our criterion from beforehand, but in a way that'll scale like we've never seen before, and that'll be built especially for the chips of our modern day like we've never seen before. And this is the part where we make a few weird things. Those few things can be optimized, and we get more to that in the later part of the lecture where we talk about blendings of convolutions and transformers. But for right now, the way that we overcome the initial issue of 224 by 224, then going into another n squared operation, is by saying it doesn't have to be 224 by 224. It could just be a 16 by 16 grid. And so what they do is they actually take an image, draw out those 16 by 16 patches, and they do just linear transformations over the flattened pixels at each of those things. And that's a very, very complicated and very, very fancy way to say they just use a convolutional layer with kernels the same size as their stride. And they fundamentally overcome the computational challenge that they had with previous image papers. And it's allowed them to transform and scale like they've never seen before with this kind of data. So the major breakthrough to take away from this paper is that you can increase your computational efficiency by rethinking the way you're feeding the data. In particular, it's finding a smarter way to downsample. ImageGPT downsampled by losing the sort of quality and like depth of its data. It went from these 24-bit pixels down into 9-bit pixels, losing a lot of the information fidelity. And the other thing that they did is they still kept the input size quite fixed, but still limited down to 64 by 64. So they made very weird downsampling trade-offs that this paper makes in a slightly smarter way. By choosing to represent it in 16 by 16, they are allowing themselves to still have a very like fine-grained, finely attentive representation layer on the initial convolution without sacrificing as much image that they do in the initial representation that ImageGPT did. And so take that as the fundamental difference. You can downscale in a much smarter way to achieve the computational efficiency you were looking for, rather than just naively quantizing your data and discarding information. Because the moment you discard information, you can never get it back. But what this paper did is they did not discard the information. Instead, they just chose a different way to do their downsampling. And that was just through a more natural convolution operation. So another fun thing about this is that, like, let's say you pre-train your transformer, you have these fixed size convolutions. There's a really, really cool result about the way that they derive their positional encoding. And that's the fact that you can actually just interpolate it. You can train, let's say, starting on 224 by 224. Then at inference time, you Google, you have a lot of money, and you're like, oh, 384 by 384 is now a more performant size because you have more information in the image. How can we go and actually adapt our model to that? You can still use the same off-the-shelf transformer that you just pre-trained. It still takes in 16 by 16 tokens. But the fun thing that you can do is just think really hard about your image positional encoding and just linearly interpolate between the initial size that you have and to the new size. And use the same model off the shelf, a little bit more fine-tuning to let it adjust to the newly derived signal. But you get an even more performant model in a quicker way without having to fully rewire everything and rethink your modeling choices along the way. And last but not least, for every computer visionist at the time, they did the one thing that everyone cared about, which is ImageNet classification. And then with one more link back to the previous paper, the only reason they're able to get most of these things is because of the pre-training. It was pre-trained on a massive data set. No one actually just trains on ImageNet and derives a model that you go and productionize or go and benchmark. You have to have some sort of other data lake that you can derive this from. And so if you're at Google, you're working on this problem, you're like, oh, let's just use JFT300M with their own 300 million images and 18,000 classes to pre-train this model. And that's what they do. They start by training on their own JFT. Then they take that model that they pre-trained on JFT, go train it on ImageNet, and that's where they get their very competitive model. And it has nice results. They get, if I remember correctly, state of the art at the time, and they train very large models, scales very nicely. You get all the things and all the niceties that you wanted out of this model, and you've unlocked a new paradigm for how to treat images. So that's good. We've gotten where we wanted. I said that we made our fundamental breakthrough, but this is only the start of it. This paper is kind of like the paradigm shift that computer vision needed to fully adopt the transformer. And I do not want to diminish its results. What this paper did is fundamentally say that we can think of images as no more than a sequence. We can use the greatest sequence representation model that we have at the time and now apply that to images. That's a big statement, not only for vision, but for just machine learning in general. If we have one solution for one task, who knows the potential it might have on another? And that's something you should be thinking about very attentively. Oftentimes another like distant field might have a breakthrough. And your first thought should be, what does that breakthrough mean to me? Don't just think it was applied to that one field, but ask yourself the question, what does that mean for me? So ruminate on that, sit on that. I made a very weird claim a week ago, and I've only halfway shown it's true. Let's go see how modern day researchers have built on that and see what we can do with it now. One more thing that we have to discuss in this paper is the inductive biases. What is at least like an ML theoretical way that we can kind of say that we have a successful solution? And why can we maybe hand wave that transformers, even on paper, would make more sense than just a convolution? Everything we've talked about so far leads us to believe convolutions are really nice. I mean, it makes sense. Like there's even like a visual or a cognitive analogy to convolutions with the visual receptive field on off in the brain. And it made sense for us so far. It was biologically inspired. It makes sense just from a neuroscience perspective. We need to at least make some sort of argument for why transformers can not only gap convolutional models, but why they can also scale so well and represent so well. And the representation mark is what gives vision transformers a victory over prior convolutional models. What vision transformers do is essentially assume less, which lets them generalize a bit more or learn much more challenging representations. But we'll get to why they actually made more assumptions later. But for right now, just stick with me and take it at face value that they made less assumptions, and that's what let them model much more challenging tasks better. So let's do a compare and contrast. ConvNets, they have locality. I mean, that feels nice, right? The most of the time, the way that we think of an image is of spatial relations, two things connected to one another. It's got a 2D like neighborhood structure, translational equivariance, you slide stuff around, it's probably the same. That all makes sense. But how do we go and derive this very foreign, very weird change that we've made? And we have to think a little bit harder and consider a little bit more, but we can actually have a fairly succinct answer that makes sense. What this paper did is it proposes image patches. So we have some sort of notion of locality, like that big conv layer that we slid across the whole entire image, that at least somewhat holds true. Many of you in the audience are probably thinking right now, it's not one and the same because they're not overlapping, and that feels icky. It does to me as well, but that's a close analog. I'll give you that one that it maybe doesn't match perfectly. Some sort of 2D structure and notion, we got that through our positional embeddings. But now, with only these few axioms, we've actually assumed far less than the CNN did. And we've assumed far less in the way that the CNN will actually do its inference. So what makes the transformer more powerful now is that we've assumed way weaker axioms to begin with. And that lets us create a more expressive, generalizable model. And so if you call back, oh, go ahead.
The positional embeddings, when you're using fingers, you like treat it as like, I guess, are the positional embeddings like one-dimensional or are they now two-dimensional?
Oh, this is a really good question. So the positional embeddings, you technically will instantiate a 1D vector more so, where it's, or like it's a 2D vector. So one vector that's added to each position. So you're right that it's 1D. In fact, you kind of like add it in a way where everything's flattened. But when you actually go and look at the way that these representations are learned, they end up having these sort of like 2D biases, even though you never told them that they should necessarily have these 2D biases. So the thing I said before about the fact that you can go and like resize your positional embeddings at the beginning, where you could like you start with like a small image, and then you go and find to model on larger images. The reason that that works is because although you added a one-dimensional, technically two-dimensional, because it's a 1D vector for every position, but 2D because you have 1D vector added to every token. You get this sort of 2D generalization if you go and do like average-based interpolation between tokens that didn't exist before. So what that kind of means in a less ambiguous way is, let's say we have like a 224 by 224 image, then we now have those like really nice positional embeddings. If we go and say we now want to do 384 by 384, within that, just consider that first row, you can actually go and stretch out that row of vectors by considering its nearest neighbors in 2D space. And the paper shows that that interpolated representation for those tokens that might not have been there before still hold and still have really good performance qualities, even though you would be correct to say we never told it that it's a 2D representation. Just the fact that each position did its own vector to be added, that's the only thing we ever told it. We didn't give it a sinusoidal function or anything weird like that other papers have done. This time we were very, very general, very liberal with it. So perfect question. Now I get back to what I was saying before about this really big emphasis that we made on pre-training. And I think this is the part where you can start to like throw tomatoes at the screen and say vision transformers and solve vision, they're still very inefficient. And that's true. So I think the claim to take away from this slide is that there's two different regimes to have within vision. One of them is low data and one of them is large data. Looking at this slide that we have on the board right now is in particular on the x-axis, they have the number of pre-training samples a model has seen. And on the y-axis, it has the 5-shot ImageNet top 1%. So just essentially it's accuracy. If you were given the top 5 predictions that a model has and seeing if it was correct in them. And the major thing to take away from this graph is that it's true, convolutions still remain more performance if you look at these ResNet models when you have lower amounts of data available. But the big reason that transformers become interesting now is because transformers edge out the slope if you take the asymptotic. If you take data as it goes to infinity, transformers are going to have a much greater curve than the CNN did. And so what actually makes this paper work under the hood wasn't the fact that they like fundamentally rethought about the way that you're taking in images. It's that they had enough data for the first time for this hypothesis to be valued. For the first time, Google had enough internal data that they could train a model using a transformer instead of convolutions that outperform convolutions. And that's big in terms of the scaling loss. So take away from this that convolutions are still better if you have limited data and you're starting from a model on maybe very few samples. At least in vision right now, very few samples means the neighborhood of like 10 million or oftentimes way less. But when you get into the asymptotics of maybe you have 300 million or a billion, which is not unheard of, there are data sets that exist open in public that you can download and use to pre-train these models, transformers start winning. And so if we're going to think about how we're going to approach vision over the next decade and think about the tools that we have at our disposal, data is one of the greatest tools. And if we're not leveraging our data sufficiently well, we're putting it to waste. The claim that I make, and the claim that I'll make about vision transformers, is that we are now using our data ever so slightly better than we were with convolutions. And that's because we're learning a more expressive function. Because we've assumed less, we suck on more data, or we suck on less data. But also because we assumed less, we are far superior on more data because our model is just that much stronger. Making more assumptions lets the convolutional models succeed in a low data regime because you overcame data by inducing bias. But the way that you can succeed in the asymptotic case is by not assuming anything and letting your model do the assumptions for you. Let your model do the expression and the functional generation for you. Don't leave that to the human. And that's the great story to take away from this slide. So basically, let everything attend to everything. That's what this paper did. That's why I say you now have a greater receptive field, is because just in the first layer of the transformer, you can let pixels that are literally entirely opposite to one another in the image communicate and relay information to the model. That's certainly not possible with a convolution, but it is now. And we've done this through a lack of inductive bias. So the inductive bias, the key thing that we assumed in the convolution is that only things that are nearby really matter to each other. That's the reason we didn't just stack a bunch of like feed-forward networks on top of each other and say that, oh, we can solve vision this way. It's because we knew deep in our hearts that there's some sort of spatial relationship to neighborhoods. And we haven't entirely lost that, but we just went a step further. We've taken the first layer, our linear projection, still assuming that spatial neighborhoods have some sort of interplay and some sort of thing to learn from them. But where we discard that is that in the very next moment, as soon as we've said, oh, two things that are close to one another should be represented together, we say that's no longer true after you've seen it once. And as soon as you've been flattened and embedded by the convolution, you're now left to see the entire image all at once instead of only looking at single small partitions of it, the way that convolutions have to do. And this is what I was getting at before by saying that we assumed less. We are no longer assuming that things have to be close together to have a relationship on the model's representations during the early and middle layers. We are now saying that anything can be related to anything, no matter the scale, as long as you've gotten past the first layer. So the key thing that we've done right there is just assumed less. We've no longer assumed that only neighboring things should be related to one another and should be related to the way that we are interpreting the image. And this is kind of like the picture that goes back to your one-dimensional vector question. If you go and you actually look at like every single representation, they map out the cosine similarity. So though what you've technically done is you've taken like your entire sequence, you've added a unique one-dimensional vector to every token in your 16 by 16 sequence. You can go and see what their cosine similarity looks like with the other positional representations, and you find that the tokens that are close together learn very similar representations, and they are often quite distant from the ones that are far away. So you've never actually told it that two things are together or that there should be some sort of local spatial bias. The model just kind of implicitly learns that over the course of time, which is a very, very interesting thing, and which is what enables the later fine-tuning task to actually succeed from. And so the word that I've been building up to the whole time is just global receptive fields. Letting everything attend to everything means that you no longer are fixed to only seeing what strided convolutions overlap with. What two convolutional layers stacked on top of each other will actually functionally represent you see. We've entirely discarded that. And we've said after the first layer, after we've flattened and linearly projected, the field is yours. And so after the first layer, you have the entire image as your global receptive field. CNNs were limited by the kernel size. Again, what I said, by whatever you can just stack in your local neighborhood. Vision transformers do not have that. And one actual study that they did in this is they looked at the queries and the keys to see what's being attended to within the image. And they showed that within just the early layer, you can see over 120 pixels apart, two different things being attended to, justifying the fact that to get a lot of information, to get a good representation of what's going on in this image, you don't necessarily need to see things that are only spaced locally, things that are only close by and like super, super tight knit in an image. You can get information from anywhere and everywhere, and you are being quite limited when you're training convolutions. And then in the final layer, you can see as the representation enriches over time, the same goes for convolutions. You're able to now see representations that were very, very far apart. So over here in like layer 24, it's basically things that were nowhere near each other just by the effect of all your features being mixed together so tightly and so agglomerated. And that's even true in convolutions. But the major difference in this graph is if you were to make a rough approximation with convolutions is that this first layer would not have such high peaks that we do here. So the takeaway is we've made less of an assumption about space, and we've now just said that the transformer can succeed by looking at the whole image. Go for it.
So are we still using causal attention now? Because in that case, I'm not understanding how we get a global receptive field for, let's say, the first token and the first attention.
Very, very good question that I did not answer due to lack of explanation on my part. You bring up a great point that if we're using a GPT style pre-training, we're like literally lobotomizing the model and telling it can only see pixels beforehand. Image GPT use a causal mask, and it's like you can only see the previous images because we're predicting the next one. But we do not use the same causal mask for vision transformers because, like you said, we now actually want to see the whole image. We no longer care about just the things that came before us. We want to see everything all at once in the same way that BERT did. BERT doesn't have a causal mask because you just want to see every token in a sentence. You don't want to just skip around and only see the previous preceding tokens. But there's contention around that. That's not the way autoregressive models work. They just use causal attention, they get away with it. But think there's arguments you can make on compression and why that succeeds there. But at least for right now, we do not restrict ourselves to having the causal mask. And every single token in the sequence can attend to every single other token in the sequence. No sort of masking to enforce otherwise. So let's talk about the cons. I was kind of bringing this up beforehand when I was talking about the way that we actually go and do these convolutions. And we have these really big patches, 16 by 16, it's arbitrary, but it feels right. We're in computer science, 2 to the something. They're not overlapping, and that fundamentally limits you to the depth of the representation that you can learn, depth of how fine-grained you can actually go and view every single task. What ImageGPT traded was they didn't want to really discard large blocks of the image, so they discarded color values and they discarded overall image size. Here, instead of discarding color values or overall image size, we just discard the number of fields that you're going to embed in an image. And so we've chosen instead to now only care about 16 by 16 grids of an image instead of the overall thing at once. And so that's what we've lost in order to solve our problem using the transformer, is we've lost the sort of fine grade representation that other models have kind of tried to preserve. This is one of the things that the CNN was able to do like very well off the shelf, is we didn't really have to assume much about our data size. We're just like, convolutions are fairly efficient. You can slide it over an image and get a computationally efficient representation throughout time. But here, we have to make a certain trade-off in order to enable the transformer to succeed. And with that, we've lost some of the fine-grained receptiveness. So, some takeaways on generality. When you move away from inductive biases, you get more generalizable, or just more general. In turn, because you've assumed less, you can say more. When you know certain things to be true, it actually restricts a model. But when you know less things to be true, you can go and say a much broader array of things. One way to think about this analogy is like an if statement versus a convnet. But now in this case, a CNN plus supervised learning is the same as an if statement versus a transformer plus unsupervised learning. Learned algorithms tend to do better if we have enough data. And then we can now also easily combine domains. One model that I care a lot about is something called CLIP, which actually takes an image and a piece of text, and it can represent it in the same vector space. And that's led to a lot of breakthroughs. In particular, it allows for something called zero-shot image classification. Throughout this whole time, we assume we know our pre-training domain ahead of time, and we also know what classes we're taking ahead of time. But let's say maybe we don't know what classes we have at the end of the day. How can we go about doing classification if I didn't tell you that it was cat versus dog? How could we imbue the natural biases and natural structure of text data in order to give something meaningful and then relate that back to the text? That's what CLIP tries to answer. And there's many more with Atari games. DeepMind just released Gato, just I think it was like a year ago, but now they're on to like Gato 2 and they're doing more. But the core thesis there was transformers. Again, what transformers have powered is the ability to take one solution from a single domain in machine learning and apply that to many different ones while keeping the architecture fixed and keeping many of the assumptions the same. And that's a very, very powerful thing because you're no longer fiddling with like what architecture, what small modeling choices do I have to make to get X to fit onto Y. You now just instead reshape the way you think about your inputs, and you can use the same solution to get you from input to output. The only question left to the researcher is what should my input look like? And all the vision transformer did is say, my input should look like this. My input should be 16 by 16 patches that I derive from convolution. And that's all. And some more takeaways. We're now moving towards self-supervised and unsupervised learning. The major thing, oh, sorry.
So you say like you lose like the fine grained detail. So like when you do the like linear layer on each of the patches, and before you like do the in the position calculation, is the output just like one scalar number? The output, or can you have like also the vectors, not like one input? And then output for like for each patch.
The output for each patch. Yeah, so the output for each patch is going to be a vector.
Okay.
So you can essentially, like, the way you actually go and implement this code is you take like a 2D convolution, and so you have 3 input channels, one for every dimension of color. Then the embedding dimensionality that you want for your transformer is just the number of output channels you'll have in your convolution. So at every single patch, you just have like a newly derived vector for each location. Yeah, really good
If
question.
you have like more, if you have like a bigger dimensional vector, would that like add more, like, would want to just be more detailed, I guess.
Yeah, that's one way to think about it. Is maybe you can fit just because you can think about all vectors the way like information passing through the model. If you have more like it's the equivalent inside of a vector, you can convey more information. And that's a perfect way to think about it. And maybe even a way to argue why like higher dimensional models will perform better is because you let them extract more fine-grained resolution within their features. And that's the perfect way to think about it. Now that you've expanded the size of your vector or expanded the transformers, like embedding dimensionality, you can encode more fine-grained representations, even just in your image embedding stuff.
Like, was that like I think that was tested in
Yeah. I'm gonna get to some results that are kind of like that. The way that people actually go about thinking about these models, what study you're proposing right now is like very particular. It's like how well it can do fine-grained like image understanding. That in particular wasn't exactly tested, but there's experiments that go in a similar direction where they discuss the overall size of the architecture and the size of like the embeddings and how that relates to performance. And we'll get to a slide on that. Sadly, not the exact question that you have, but I don't exactly know the certain paper that answers that. If I find one, I can like try to think of it and send it to Ari, but you're thinking like something very, very important, very, very fundamental. That would be cool to see numbers on. And yeah, the major takeaway about generality and why transformers succeeded is just a story of data. We need a lot of data before we could finally make the transformer actually beat out the convolution. Because until we had a big enough N, convolutions were still lapping us, like by miles. Like, I don't think I emphasize enough just how bad this is. Like every single transformer was like 20 to 30% worse than a convolution. And these are like the days where you're really questioning, like, why am I doing research if I had an off-the-shelf existing solution that worked so much better? And what actually changed their point of failure into a point of success was just the data. And in particular, the slope that you see when you scale up the data. So again, transformers are a story of reshaping and rethinking about the way that an image can be understood, but also a lot of it is just being rich and having enough data. Sometimes not talked about too much machine learning, or if you're on Twitter, maybe talked about too much. Machine learning has a great dependency on compute, and compute is a function of how much data can you process all at once. And if you can process more data all at once, you're going to do better. And I wish I could give a better statement beyond that, but that's one of the places that academia shines, is that that's maybe the only place where people are studying how can you be better by using less computation. So take all of this with a grain of salt, but you should begin seeing some general patterns emerge by this transformer style of thinking. You need a lot of data, and you need a hell of a lot of GPUs or TPUs to make this data turn into something magical. So transformers give us generality, where biases are learned from data instead of handcrafted. Convolutions, we handcrafted our biases to actually go and convolve across the image, have a sliding filter. But with transformers, we're like, we convolve once, let the model learn the rest, and that leads to a more expressive learner. But again, this goes back to data. This only is useful if we have enough data where you can learn enough features that make relaxing your assumption worthwhile. So keep in mind the interplay of assumptions and data. Making more assumptions works well if you have less data. But if you have a lot of data, maybe try making less and seeing what your model can tell you that you couldn't have told it. And by the way, bits are really good. They're lapping like everything on the boards. So there is no reason, at least in the modern day, if you're trying to go for like top of the top best ImageNet performing classifier, that you should not be using a transformer-based model. These things scale so well on the cards, it's honestly like magic if you go and watch some of these things train. And time again, we see on literally every task, these models just dominate. So if you go, I believe these are like the current state-of-the-art models. Model Soups is one of my favorite ones. Those come from some friends of mine. They have a cool idea where if you take a bunch of models that have all been like fine-tuned on the same data, and you end with a really good resulting model, you can go and fine-tune that good resulting model a few times over, then average together those models and get an even better model by the assumption that you actually were in a small bowl by the end of your training. You're in some sort of local loss basin where stochastic gradient descent lets you just hit different levels on that bowl. But if you average all those levels together, you can actually get a point that's closer to the bottom. That's just a fun aside. And that thing was a mixture of convolution and transformer to go and succeed. But if you look at this table, take away the fact that we now have a hell of a lot more parameters, billion plus. The reason we didn't see that with like ResNets is because they're hard to scale. They're fairly unstable. And having many deep convolutional layers is just expensive too. But now we're scaling like we've never seen before. And everything is using transformer, or at least convolution plus transformer, which we'll get into a little bit more. And by the way, the data sets have not gotten smaller. JFT3B is huge. Could you imagine having 3 billion actually classified images? Like you can scrape a ton of data from the internet. There is an open scale data set called Lion5B that has 5 billion images with textual captions associated with them, but they don't have the exact same kind of like particularness that an image classification task has. It's more of like an open vocabulary image understanding kind of thing. And from now, we've kind of taken transformers from cool in theory. I made a bunch of claims and a bunch of arguments about a week ago today, to now being state of the art. I've put my money where my mouth is, and I've shown you that these things quantitatively are outperforming everything we've talked about so far in vision. So let's go and see how else they're doing. The story goes that compute goes burr. Jared Kaplan over at OpenAI, I think it was 2019, he published foundational work, which basically says, if you have a language model and you make it bigger, if you make the data bigger or you make the parameter bigger, the number goes up. Actually, they were using loss at the time, so loss goes down. So everything you'd see is down and to the right. And if you have more data, you go down and to the right. If you have more parameters, you go down and to the right. This is the great story that's been like, we've kind of solved the fundamental problem in the field. Let's just go and throw a bunch of money at it to see how good we can really do. And so scaling vision transformers is the equivalent of that, not for text, but now just for vision transformers. So they use the same exact architecture, and they have a little bit of insights into scaling. Better representation scales with compute, time, model size, data set size, and large models are more sample efficient, which is actually a pretty fun result. You can train large models with less data and have them be higher performance than small models with less data. And then lots of small engineering things, 2 billion parameter, ImageNet state of the art at the time, fun stuff. And this is like the foundational graph to look at in the paper. And I'll go into an aside on why this is kind of a very different line of thinking from a lot of modern machine learning research, and why, although I kind of say it just goes down to the left, there's a lot more to be thought about this. On the x-axis, we go with TPU v3 core days. TPU, GPU, they're close enough to the same thing, fundamental differences, whatever. Just know it's compute on the bottom axis and ImageNet error on the y-axis. And so the relationship you can see here is just the more compute you use, the better your error rate is, or the worse your error rate is, which is good. Blue models are the small models. You can see them at the top left of the graph, but the smaller actual dot sizes are the smaller data sets. And so this paper went and investigated is how many of these things, when like compared to one another, will actually go in effect along the Pareto frontier, which is like your optimal image error per compute used. And fairly simple takeaway from this graph. I can't extrapolate too much more interesting beyond the fact that if you scale up amongst model size or amongst data set size, you see very interesting phenomena. But the part where I'll give this some justice comes to a conversation I had with Ashish Vaswani, and he compared this to actually physics. Ashish Vaswani was the first author on the attention paper. Many of them were just joint authors, but he gives a lot of thought to these kinds of things and a lot of the scaling, and he doesn't discard it nearly as readily as one might if they just look at this graph and say, oh, more money and you get better performance. We're now stepping into a realm of understanding of these models where it becomes akin to physics. We're observing the natural phenomenon that happens when we go and we tweak some of these parameters in the model, and it's like we're just observing the universe and observing performance. It's no longer us engineering something new and seeing if we can outperform our competitor. It's observing what these models can do at their present state and seeing how they behave on new and wild different data and scaling frontiers. So although I say it in jest that it just goes down to the left, there's a little bit more credit that should be given to them. Perfect. Yeah, the only major interesting takeaway is that you can kind of combine transformers with convolutions just through some more steps, basically at the early part of the network. And if you do a little more convolutions, you can squash your representation a little more. That allows for a more fine-grained representation where If you just actually do more convolutions instead of doing like that really heavy-handed, non-overlapping 16 by 16 patches, you can preserve that information a little bit better. And I think, at least right now, those models are still outperforming pure transformers alone. There's a little bit of contention there in the community around that because it's not too crazy yet, but they have some nice inductive bias scaling as well as the fun niceties of transformers.
You will actually implement Boolean transformers on 1.3. That's coming out next week. So yeah, I haven't finished it today, but I'm gonna get a chance to play around with it. So next week.
Like, maybe from, like,
This one?
yeah, does that just mean like more computation? Do you just do like more view? You look at the same data.
So it's a mixture of that. Some of it's more like epics, some of it is the more like literal compute units you like glue together. So these models are really expensive to instantiate in memory, let alone take the gradient of. So it's a lot of things all coagulating together. Because when you just have like a larger model, doing the forward pass takes that much longer because we're bigger. And so it's not only just doing more epics, just doing more samples. It's sometimes the fact that like bigger things took longer to achieve the same number of samples as a smaller model.
Oh, yeah, so it's not like, not slightly different, but it could be just like.
Yeah, it could be like a bunch of things. It could be, yeah, like one thing you talk about is a very real thing where they literally just ask like, what if you train it longer and it works better? Yeah, so that's something that like makes TPUV 3 days like a good proxy for seeing how you scale with compute, but not yet something perfect to like claim on.
The bigger model you have, you actually run less. So like, if you look at these big LLMs, they don't even do like one full epoch. I don't know if that falls for these like large transformers.
Is one epoch, does that mean like when you see all the data?
Yeah,
Correct.
even that also holds for.
I don't think we've hit that scaling
Yeah,
yet.
even.
And there's even an argument to be made amongst language models that like you shouldn't be stopping them before an epic. Like a lot of chinchilla optimal stuff, like, ooh, train long, loss keeps going down. You're too impatient.
But that's
More
actually-
R&D money.
Goes through for MAE, like it does what next week,
That'd be nice.
but they show that it keeps getting better and better as you just keep training on the loss.
I mean, that's like, I mean, yeah, still scaling well, but I mean,